Good afternoon. Today is Thursday, October 3rd. I'm hoping that you guys are watching this video on Monday, October 7th at 8 a.m. during our regular CC session, because we do not have Class Connect until Wednesday the 9th, and your unit exam is due on Thursday the 10th. So if you are watching this video and you are watching it before Monday the 7th, congratulations to you. I just wanted to go over some of the most important concepts that you are going to see on your Unit 1 exam. We are going to be going over everything from week 1 to week 7. So if you are watching this video, I would highly suggest that you take out a pen and a paper, or maybe a Word document, and take notes so that you can refer to them when you are taking your final. Moving forward, important things to know about the test. Understand that it is timed. You have 90 minutes to complete it. The test is worth 39.5 points. It accounts for 35% of your total grade because it is again a test. It will cover everything from week 1 to week 7. You have one attempt, so do not come and try to start taking your test until you have 90 minutes to dedicate to it. It is enforced, and it will stop, and it will not let you make corrections. I have questions on there. There's only 3 of them that are coming from Unit 2 that we have not went and gotten into. I just wanted to give you guys a little test to see how much you know about the unit that's going to be coming up. So those 3 questions at the very end of your test will not count towards your grade. So just answer them to the best of your ability, but do not worry about the fact that you may not know the answers to them, and that's okay. So moving into the very first week, we started talking about atoms, and we used this image to try to get you guys a visual of important things in regards to the subatomic particles. Remember that protons are positively charged, and they are located in the center of the nucleus, which is here, as well as neutrons, and those do not have a charge. Also remember that electrons are negatively charged, and they are located out here in the orbitals. Sometimes we call them clouds, sometimes we call them energy levels, but at any rate, this is a depiction of what an atom looks like. Here is your nucleus, and here are your electrons. We then made connections between the idea that we have elements, and we know that every element has the same type of atom. And then if we're going smaller downscale, within the atom you have a nucleus, and within the nucleus you have protons. We moved on to the idea that these protons are associated with an atomic number that you could find here on the periodic table of elements. And also remember that your proton or your atomic number is going to determine what kind of element you have. So we know that this element of hydrogen is hydrogen because its atomic number is 1. If the atomic number was to change to something else, like let's say this atomic number changed to 10, then the element would change itself. So this atomic number is very important to understanding that it's going to determine an atom's identity. And it also helps us because the periodic table of elements is organized by these atomic numbers as well. We had questions that were very important for us to be able to understand. That an element is the same substance made up entirely from the same type of atom. So if you have a hydrogen element, then it is made up of hydrogen atoms. We also had a conversation about what an atom's mass number is. I apologize. And a mass number is just the number of protons and neutrons within the nucleus. And you will have to calculate the number of neutrons in an atom, so just remember that you have to take your atomic mass and subtract it from your atomic number to be able to get your neutrons. And that can be done with the use of your periodic table of elements. If you are taking the test, make sure you have a periodic table of elements. You will need it. So the atomic number is located here, here, and here. It tells us the number of protons in the nucleus. We learned later on that it also tells us the number of electrons as well. The atomic mass number is located at the bottom, and this number just tells us the number of protons and neutrons, and again, that is the weight of the atom or the weight of its nucleus. And then again, here is just a pictorial representation of how do you calculate the number of neutrons. We talked about the average atomic mass. I am not going to have you do this calculation in your exam, hooray for you, but we do need to know that isotopes happen because there's a change of the number of neutrons, which again changes its atomic mass. If this mass tells us the number of protons and neutrons together, and we're saying that an isotope changes when its neutrons change, then essentially this mass number is going to change as well. You will be seeing things that are in isotope notation, so just remember, very importantly, that things are flipped here, okay? So when we look at the periodic table of elements, our atomic number is here and our atomic mass is here. But when we move into isotope notation, it's switched. Our mass number's on the top and our atomic number's on the bottom. That's just something to always remember. And when we are writing things in isotope notation, whatever is after the actual element is its mass number. So neon 2210, that means neon has an atomic mass of 22 and it has 10 protons, that's its atomic number. And we would write this isotope as neon 22. We did some gizmos. Just be familiar and comfortable with knowing that if I give you an isotope, like chloron 35, that its symbol would be chlorine, that its mass is always here, and then you could figure out how many protons it had by looking at this symbol in the periodic table of elements and finding that its atomic number or the number of protons is 17, and then you could do math and you could take your mass number and subtract it from the number of protons to get your neutrons. So be familiar with making these calculations as I will ask you to do them. The next thing we started talking about were periods and groups. Remember that periods are going along horizontally and that groups are going down vertically. We can also think about the trends within the periodic table of elements. So please, there's a lot of questions about stuff like this. Be comfortable with knowing that if you have, if you're looking at things that are in periods, that they have the same number of orbitals, and that if you are looking at things in groups, that they have similar properties and similar valence electrons, which means those electrons in the outer orbital are going to be the same. We then went into it even more and said that when we're looking at atomic size, as you move to the right, your atomic size is going to be getting smaller. Your ionization energy is higher as you move to the right, and your electronegativity increases as you move to the right. When we look at groups, atoms get bigger as you move down because again, they're going to have more orbitals, so they're going to be bigger. Your ionization energy as you move up is going to be higher. Okay, your ionization energy is just the ability to be able to pull an electron from you. And then your electronegativity decreases, and again, just think about it in terms of the orbitals. If I am a nucleus and I have 5 orbitals and I have electrons that are farther away from me, then my electronegativity is going to be down because I don't have such a great grasp or an attraction to those electrons that are farther away from me. I love this slide. This was kind of like your exit ticket for the standard. Could you guys understand the trends in the periodic table of elements, that your atomic radius decreases as you move to the right. Ionization energy increases as you move to the right. Electronegativity as well increases as you move to the right. And then your radius increases as you go down. So does electronegativity and so does ionization energy. If you understand the trends that are happening here, then you should be pretty good. We then moved into our second standard, high school physical science 1-8, and we started talking about different kinds of nuclear energy. We started off with alpha decay. Please be familiar with the idea that we have a nucleus, and when it alpha decays, it emits a helium particle. Remember isotope notation. This is telling you that it has 2 protons and an atomic mass of 4. So 2 protons and 2 neutrons within its nucleus. Okay. Be familiar with the idea that you need to know how to balance chemical equations and identify them. So knowing that you have some sort of an isotope who is unstable because it has too many protons and neutrons, and that it's going to alpha decay, it's going to become something new, and it's going to have that alpha particle at the end of it. This is just another really easy way to understand it. If you know what element you are, and in this case it's uranium, and you're going through alpha decay, you're automatically knowing that you are going to be losing 2 protons, and that means we're moving down the periodic table of elements. Remember, if we have 92 protons because we're uranium, and we go through alpha decay, which means I'm losing 2 of those protons, then boom, this is how I turn into thorium 90, 2 to 90, and then your mass number is going to change as well, because the mass of the helium atom was 4, so 238 minus 4 turns into 234. So please be familiar with identifying these and understanding the mass and the protons when you go through alpha decay. Then we moved into beta decay. I know there's a lot of stuff going on here. Oh, I guess we're still in helium, sorry. So just being familiar with the idea that you have an isotope, and when it alpha decays, you're always going to get rid of this helium, and then you should be able to figure out what products you have just by simply doing math. 237 minus 4 gives you 233. 93 minus 2 gives you 91. And as long as you can figure out these 2 numbers, you can figure out what element it is by looking for this number in the periodic table of elements. So please be familiar with that. If you're not, go breeze up on it. Then we moved to beta decay. Beta decay was a little bit differently here, because when we talk about beta decay, the mass does not change, okay? And the reason our mass does not change is because we're not emitting anything from our nucleus here. We emit an electron, but we don't care about electrons when we're talking about the mass of an atom, because remember, the mass of an atom is within its nucleus. Your electrons are in those orbitals, so they do not matter. A lot of you guys missed this question on your gizmo. So if you're asked about why the mass of the isotopes do not change when we're going through beta decay, it's because we're not emitting anything from the nucleus. What's happening is you are changing one of your neutrons into a proton, okay? And remember, your protons are what make you the element that you are. So if this carbon had 6 protons, and it gave up a neutron that turned into a proton, then our number changes here. The 6 turns into a 7 because now I have 7 protons, which means I have a new element. So be comfortable with this idea. You can use the periodic table of elements the same way, and understanding that your protons are here at 90, which puts us here. Well, if you go through beta decay, one of your neutrons turns into a proton, boom, and that means our atomic number is changing and we become a new isotope. You will have matching on your final, and you will have to look at different kinds of equations and decide if they're beta. Just remember that your beta particle has no mass and it has a charge of -1, which is different from your alpha. I have these videos for nuclear fission and nuclear fusion linked. Remember that the first step in nuclear fission is that a neutron is going to hit a nucleus. A lot of you guys missed this. Remember that nuclear fission is basically the breaking apart of an isotope, and it releases a lot of energy, and it's a chain reaction. Be familiar with the idea that you're going to have to identify these chemical equations here. And for nuclear fusion, that's completely different. Fusion is when we take 2 smaller nuclei, we put them together to make a bigger one, okay? And fission is the opposite. We're breaking something apart. Again, those videos are there. Be familiar with the idea that when we're talking about fusion, that you're going to have neutrons as products. And this is our schedule. I hope this helped.